Hello, everyone. The title of my brief talk is Influence of Short-Term Post-Welding Heat Treatment on Corrosion Resistance of UNS N06625 Superalloy. Co-authors are Professor Alberto Fabrizi, Franco Bonollo, and Filippo Berto. These are the contents of my presentation. I will start with a brief introduction, then I will go ahead with the experiment. I will describe the results and a short discussion, and finally, of course, the conclusion. About UNS N06625, I have to say that it is a nickel-based superalloy that was developed in order to have a good resistance, high resistance against high temperature, aggressive environments, and so on. For example, high temperature oxidizing environment, seawater. So the problem that we have when we have to weld these alloys is the problem that we have in general when we have to weld alloy with a very complex chemical composition. In particular, using fusion welding, we are going to destroy the optimal microstructure and induce the precipitation of secondary phases, such as delta phases in this case, that are detrimental for the corrosion properties of the welded joints. This phenomenon is called sensitization, as in stainless steel, for example. So it is, mandatory to perform post-welding heat treatments in order to restore both the mechanical and corrosion properties of this alloy. Unfortunately, no consolidated data are available in the literature and in the industry regarding the best process parameter, in particular the temperature and the holding time. So the goal of this work was to study the effects of the temperature in the post-welding heat treatments, to study the influence of such parameters on corrosion property, in general, to find the best process parameter in order to restore corrosion properties of these welded joints. This table collects the nominal composition of the alloy. I have highlighted in green the most important element, the key element for corrosion properties. In particular, nickel and chromium are used against oxidizing environments at high temperature, and while molybdenum and niobium are used against local corrosion. These two pictures show the workpieces that we studied. There are pipes, tubes obtained by sheet forming and then welded using longitudinal welding. The longitudinal welding was performed with the two runs, two passes. The first pass was carried out with a plasma arc welding, and the second pass was carried out using gas tungsten arc welding. This table collects the main important welding process parameter used in this experiment. After welding, we perform, of course, post-welding heat treatments using two different temperatures, 980 degree and 1050 degree, and we keep the holding time constant and equal to 20 minutes. We perform also corrosion tests according to STM G28, the method A, and then we carry out metallographic investigation in the three most important zones of the joints, the fusion zone, the heat affecting zone, and the parametal, using optical microscope, scanning electron microscope with EDS in order to investigate the redistribution of the key elements in the welded joints. These are the results in terms of micrograph, SEM micrograph of the as welded joints. We observe a coarsening, a grain coarsening in the heat affecting zone as expected, and a dendritic microstructure in the fusion zone. We also found different precipitate. The dark colored precipitate were identified as oxide. On the other hand, the light colored precipitate were identified as carbide enriched in niobium and molybdenum. Moving to the microstructure of the post-welded heat-treated joint at 980 degrees. We observe more or less the same microstructure of this welded joint with a variation in the morphology of the carbides that now appears as grain boundary film, as you can see in the heat affecting zone micrograph. Moving to the microstructure of the post-welded heat-treated joint at 1050 degrees, we observe, of course, the same microstructure and as in the previous case, but now the carbides returns to be equiaxic in shape. About the redistribution of the elements, the most important elements for the corrosion resistance, we perform EDS line scan through the secondary dendrite arm spacing, and we found a segregation of niobium and molybdenum in the interdendritic zones, and in the opposite way, nickel was depleted in this zone. This is the distribution of the element in the as welded joint. By moving to the post-welded heat-treated joint at 900 degrees, 80 degrees, we observe that we have little reductions of such kind of segregation. So have a partial redistribution. And by moving to the samples heat-treated at 1050 degrees, we observe a homogeneous distribution of the key elements. So these are the results of corrosion tests. In particular, we can observe that the post-welded heat-treated joints behave better than the as-welded joints. So post-welded heat treatment were effective in order to restore more or less the corrosion resistance of these alloys, and the best results are obtained with the highest temperature, 1050 degrees. We also observe that the corrosion attack occurs in the interdendritic zone of the fusion zone. Okay, about the discussion, we have postulated that in the interdendritic zone we have a precipitation of secondary phases. Okay, delta phase precipitate in the interdendritic zone with a nanometric size. This is also it was observed also in literature, and this is the problem of the corrosion of the or the systemization of as welded joint. Using a post-welded heat treatment, we can observe that we are able to redistribute this such element. We have a partial solubilization of delta phase, but at this temperature, 980 degrees, only a partial solubilization. On the other hand, with this temperature, with the highest temperature, we can reach the best result, because we postulate that we have a complete solubilization of secondary phases, so a complete restoring of corrosion resistance of this alloy. This is for both a kinetic reason and for a thermodynamic reason. Okay, this has the conclusions. We have found the best temperature for the heat treatment. Thank you very much for your attention.